this talk is to show an extension of the celebrated result by Bartnik and Simon about the existence of space-like graph with prescribed mean curvature on bounding domain in Minkowski spacetime. Our extension consists in replacing the bounded domain with an exterior domain. This means the complement of a bounded domain, if you want, but also something more general. So this is a work in collaboration with my colleagues Rossella Bartolo and Alessio Caponio. I will consider the n+1 dimensional Minkowski spacetime and a domain omega, which is given by the union of bounded disjoint Lipschitz domain omega I here. So this is not the domain that we are going to consider, but we will consider the exterior domain omega C, which is the complement with respect to Rn of this domain omega. So the equation, we want to solve this equation, which is the equation for a solution of this equation as graph which is space-like if the gradient of u is everywhere less as norm everywhere less than 1, and here h is the a function on the Minkowski spacetime which represents the mean curvature. So the mean curvature is prescribed, is assigned a priori. We want we ask also for a solution that assume the value phi on the boundary and vanish at infinity. So a bit of history of this equation, as I said before, for when omega is a bounded domain and you look for solution in omega, which coincides with the datum phi on the boundary. So if you want to solve this Dirichlet problem, in the Minkowski spacetime, I think that the first result is due to Bartnik and Simon in this in the paper, in that famous paper in '82, and in that paper the authors don't have assumption on omega and on the boundary of omega. So omega could be any bounded domain, any open connected subset of Rn, while the datum phi must be extendable to a function which is space-like in a weak sense, a sense that I will specify in a few minutes. And so the only condition that they put is that there exists the limit of psi of this extension. It's better to say this, that the extension must satisfy, is an extension in this sense. There exists the limit of the function psi when you consider any open straight line segment in omega with endpoint at point x0 that you have taken on the boundary. So this is the only condition that they put. So this result was soon after reconsidered by Gerhard in '83, and he proved the existence of solution for the Dirichlet problem in a more general ambient space. He considered an orthogonal splitting Lorentzian manifold. Actually, in the results by Gerhard, omega must be a C2 domain, so a domain with a C2 boundary. And after this result, Bartnik also considered a more general class of spacetime, the ones that admit a global temporal function. And finally, in his celebrated results on Acta Mathematica, he gave also a more intrinsic result where no global temporal function is assumed to exist on the space-time. So what about results on an exterior domain? So when omega is replaced by the complement of a bounded open subset, we have a couple of very recent results. One that appeared last year on Communication Pre-Applied Mathematics, where the authors proved that there always exists a maximal hypersurface, so for h equal to 0 in that case, for any given asymptotic profile of this type. So they are able to show that there exists a solution with of the Dirichlet problem defined on the exterior domain when this solution at infinity goes in this way. There is another result on the journal differential equation where the authors prove existence and multiplicity results for a radial solution outside the ball. In the previous result the domain is the exterior domain is whatever you want. In this case, in these other results, the exterior domain is the complement of a ball, and they consider homogeneous boundary conditions. So phi is equal to 0 in these results, and h is of course radial as well. What are our assumptions? So the first assumption concerns the dimension. So we consider n not less than 3. So the Minkowski space-time must have dimension at least 4, which is good for physical purposes. And this is due to this is a technical assumption because we need some, we'll consider this space here, D1, 2, which is the completion of the space of smooth function with compact support in omega c, with respect to the L2 norm of the gradient. So this space is embedded continuously in L2 star, where 2 star is the critical Sobolev exponent given by 2n over n minus 2. So and it must be greater than 3 for this embedding. And what about the function h? We assume that h is controlled from above by a function which depends only on x, and which is in ls omega c, so its power s is integrable and locally bounded. So here S is an exponent between 1 and 2n over n plus 2. Finally, what about the datum phi? Phi must be our proof is variational, so we work in a certain functional space where we try to minimize a function that I will show later. So we ask that phi is the trace in the Sobolev sense of a function in this space of function that we consider. But a posteriori, we will see that phi must be a Lipschitz function. And moreover, if omega, so the complement of omega c, is not convex, which happens, for example, if there are two connected components at least, we ask that phi is space-like displacing, which means that for any x and y in the boundary, if the segment between x and y is contained in omega c, then this inequality must be satisfied. That means that if you consider the segment in the Minkowski space between x phi of x and y phi of y, this must be a space-like segment. This is the same assumption that Bartnik and Simon assumed for the extension psi or the datum phi. So they say in their paper that psi is space-like in this sense here. Okay, so for us will be this notion will be called space-like displacing in order to reserve the word space-like to the what is commonly known as space-like. I mean an hypersurfaces which is at least C1 and whose tangent space are always space-like. So this is our result. So under the previous assumption, we can say that there exists a space-like weak solution, in the sense that this weak form of the equation is satisfied, which is a C1 function whose graph is space-like. Some comments about these results are the following. Actually, under our assumption H, if there exists a space-like weak solution of the problem P, then the datum must be space-like displacing. So in some sense, we have a sufficient necessary condition. Of course, it must be space-like whenever omega is not convex. Also, this is standard, quite standard. If H is continuous, then the solution is C2 is a classical solution. It's not only a weak solution. It's C2 inside omega C, and also, this is well known. If H is non-decreasing in T, so the solution is also unique. We can also say that whenever the phi is 1 minus epsilon Lipschitz continuous, then there exists a space-like solution, because in this case we can prove that phi is actually the trace of some function in the space that we consider in our variational setting. So the idea is to minimize this functional here I, where G here is a primitive of the function H, and I will call this part of the function I naught. So this is not exactly the function that you will consider in this situation. Maybe it is you will delete this put a minus here, but observe this one here. But observe that this is convenient to consider this this function, because we have that the integrand here is controlled from above by the square of the gradient. So if you have a gradient in L2, I naught is well defined, and moreover is controlled from below by this by 1/2 the gradient of u to the square, and this is important for the coercivity of the coerciveness of the functional I. So this functional I naught comes from Born-Infeld energy functional in the nonlinear electromagnetic theory due to Born-Infeld. Actually, this is a very simple case where there is no magnetic field, and so this is U in Born-Infeld theory represents the electric potential in the electrostatic case. There is also a parameter B in the Born-Infeld energy function, but we will assume V is equal to 1. So we don't need it. Born-Infeld theory gained some new interest in the 90s, in particular in the community of physicists working in string theory. And in particular, I will suggest this paper by Hinson Yang that I think influenced also some subsequent works by mathematicians. And this other paper by Kiesling on communication mathematical physics, where he found maximal space-like hypersurface defined by function defined on wall Rn minus a finite number of points where the function, where the graph has light cone singularities. So after these results, other people used the functional I written this way to prove existence of radial solution for the Dirichlet problem. And in particular, in this paper in 2014, Bereano, Belen, and Moen considered were able to find a couple of solutions for the Dirichlet problem, so two solutions in a bounded domain via no-smooth critical theory. Of course, H has a spatial expression in that results. But after these results, other mathematicians use this functional I, Bonner, D'Avegna, Caponio, Jacopetti in different works, found solution in Rn when H is possibly unbounded, also a measure. So H don't, I think in their results do not depend on T. So what is the space? The idea is to minimize this functional on this set here, x of phi, which is given by all the function u on defined on the space x, whose trace in the sense of Sobolev spaces is equal to the datum phi. So here x is given by these intersections, where W dot 1, 2 is the homogeneous Sobolev space of distribution with partial derivatives in L2. So only the partial derivatives are in L2. And we intersect this space with the space of L2 function, L2 star function, and with the space of locally Lipschitz function with the gradient bounded by 1. Notice that this intersection here is related to the space D12 that I mentioned at the beginning, the completion of the space of smooth function with compass support. Indeed, it can be proved that this space here is given by the function in W dot 1, 2, which are also in L2 star, and whose trace is equal to 0. So this space D12 plays an important role by this equality here. Then we have this lemma. So consider x naught, which is the space x phi when the datum is 0. So x naught is by this equality here is a subspace of the Hilbert space D12. This is an Hilbert space, and it satisfies the following properties. It is continuously embedded in the Sobolev space W1P for all P greater than the critical exponents, and it is continuously embedded in the space of bounded function. Moreover, all the elements in x naught goes to 0 at infinity. Clearly, it is convex also and weakly closed, and moreover, it is sequentially weakly compact. and also any bounded sequence in X0 admits a subsequence with converge uniformly. So we have a lot of properties. I must say that this result is due to Bonner, D'Aveni, and Pomponio when omega c is equal to Rn. So we have also this other lemma which say that actually a locally Lipschitz function with bounded gradient, due to the fact that omega c is has a boundary which is the same boundary of omega, so it is a Lipschitz boundary. So due to this fact, any function which is locally Lipschitz with gradient bounded admits a Lipschitz extension to the closure of omega c. So if you want to the whole Rn, then if you take a function in X, you can extend by what I said before it to a function U bar, which is then in D1, 2, and it is a genuinely Lipschitz function, not only locally Lipschitz on the whole Rn. And then by the above result, U bar, this extension is in W1P for all P between 2 star and plus infinity, and vanishes at infinity also. So now if you take a function in X phi, clearly you can describe X phi as the sum of any function in itself plus the space X0. By the lemma above, we have that X phi is convex, weakly closed, and moreover, any bounded sequence admits a weakly converging subsequence, which uniformly converge on compact subset of omega c. So this is, of course, a nice property if we have that I is also weakly lower semi-continuous, continuous, and coercive, sorry. And this is the case because I is given by the sum of these two functions. The second term here can be shown thanks to our assumption, H that that it is sequentially weakly continuous. Since I naught is convex and strongly continuous with respect to the L, say the L2 convergence of the gradient. So we get that I is actually weakly lower semi-continuous and coercive. So there exists a minimum of this function on X phi. So this minimum is a weakly space-like. So it could have some points or some regions where the gradient has norm equal to 1. But we can then use several known results essentially proved in the paper by Bartnik and Simon about local properties of this minimizer. The first property is that the minimizer must be a C1, actually C1 alpha locally. And also a minimizer must minimize this functional here, which is obtained by replacing H by this function H star, which is given by H evaluated on the minimizer U, so on the function X on U of X, okay? So it can be easily proved that it must be a minimizer also for this function. And then you can use so-called
time is almost finishing.
Yeah, this is the last slide.
Okay, thank you.
Yes, you can use the null segment condition in Bartnik and Simon paper. So, apply to minimizer of the functional I star. So if there Bartnik and Simon proved that things can go wrong in the sense that a minimizer can have a graph which contains some null segment, like segment, not regions, so not single point, but like segment. But if this happens, then the segment must reach the boundary of omega c, or in our case, infinity. But both these possibilities are can be avoided by our assumption. The first one by the fact that phi is space-like displacing, and of course the second one by the fact that u vanishes at infinity. So the minimizer is actually space-like, and it is a weak solution of our problem. Okay, this is all. Thank you.